Hello, I'm John Lee. I'm a wood quality scientist from Scion in Rotorua, and today I'll be presenting on the DiskBot, which is a wood quality scanning system developed by us. So the DiskBot, a wood quality scanning system. What is wood quality? During wood formation, numerous factors, both inside and outside the tree, lead to variation in the type, number, size, shape, physical structure, and chemical composition of the wood elements. Wood formation is the process, but wood quality is the result. So what is the DiskBot system? On the left, basically, it's a bunch of sensors and cameras bolted together with a slot pro frame parked on top of a Parker XY moving table. And what does it measure? It's an array of scanning sensors or stations that measure or infer wood quality traits both directly and indirectly. We have X-ray, which measures wood density, NIR or near infrared, which measures wood chemistry, USV or ultrasonic velocity, which is a measure of stiffness or microfibril angle, and MLT, which is masked light transmission, which is basically a bright light shine through the disc and the light follows the fibers, which gives us a grain angle. Here we have a picture of the DiskBot in action. The discs are loaded into the green cassette that is then placed into the robot system. Here we have the USV being measured. The disc passes between two probes which send an ultrasonic sound between them. It covers the entire surface of the disc. The same process is used for all of the other sensors where the robot travels the sample under the sensors themselves. All the data then is automatically just packaged together and sent off to a cloud database. And then a new sample is added. The scanning takes around any between 8 and 15 minutes, depending on the size of the sample. When we talk about wood quality models, in the past, there generally were average models of wood quality. So we would look at a bunch of cores for an area or a site and produce basically wood quality distributions where we had low density at the pith, and it gets better as you get out and with age. We know that there is no average tree. When a tree goes to the sawmill, it has particular bits of peculiarities in it, compression wood, changes in density, changes in stiffness, changes in grain angle, all these things that we can't readily see. We also know about growth rate and tree shape and tree architecture. The bit that the DiskBot wants to put into that is to be able to infer that variation so that we can then model trees that are more likely to reflect the actual tree in the forest. Now, when we talk about the real variation, these are the vertical lines. Each one is a stem, 21 stems here. And these are discs taken every 1 meter up the stem, all on the same site, all the same age. So you can see there's a huge amount of variation in shape and size and distributions. These are photo image of some green discs just after they've been surfaced. While everything's green, we can see a few things. We can see the heartwood, we can see the ring boundaries, and we can see in this case some patches of compression wood. As the discs dry out, we tend to lose the ability to see these things. And our DiskBot runs on dry discs. There's other factors we of course can't see, the chemistry, the density, the stiffness, patterns across those disc areas. These are scanned images from the disc. From the left to right, we have density, the middle one galactan, and the right-hand side is the USV. So we can see the distributions across those. Interesting, the galactan one, the discs that you saw just before this, you can see the compression wood, the light blue area showing up quite well there. Also, in the USV, the same area is a dark blue. So you've got high stiffness, but also high compression wood in the same area. That would make some interesting timber. Additional applications being developed with the CoreBot. So basically we've altered it to measure 12 mil cores, and at the moment scanning for only density and the near infrared. We've tried to automate the ring boundary allocation. We're looking at identifying heartwood development in dry wood. And we've looked at small modified wood samples and going to be looking at other species like cypresses, totara, and eucalypts. Here's an example of the corbot bark to pith scan spark on the left, coming to the right. This is lignan, so you can also already see that there's quite a variation. So you can start to actually quickly and cheaply look at trees and make an assessment whether maybe you need to take a full disc or live with some more average properties. Ring digitization. It's usually quite nice to know when the thinning was happened or a fertilizer was put on and what the results of those things were, or if there's been some sort of climatic change that may have affected growth. We can go back by a year. Currently, we've been manually doing this. It's very slow. It can take up to 20 minutes to do a large disc, and we're prone to human errors where people see things differently. An automatic approach has been developed, fast batch processing using the disc density data. Here in the yellow, we have density scans, and what we've done is taken radial paths from the pith to the bark and taken the density data from those radial scans. We've taken those every 5 degrees around the stem. Each of these vertical lines is a representation of those radial strips, and using mathematics and working the front edge of every one of the clumps where it makes sense, we're able to link those together and give us the ring boundaries. Why are we doing this? We'd like to understand the connection between genetics, environment, the site, and the end product quality. So feeding data into our next generation wood quality models. Improve the confidence of processors in the resource coming on stream. Early quality assessments of stands pre-harvest. Provide recommendations on how to grow better wood quality or better wood in the future, and help tree breeders target improved product quality outcomes, and provide a framework for growers and processors to have a conversation about benefit sharing. So what's good for the processor might be good for the grower. This has been a long project, up to 7 years, and a lot of people have come and gone. These are just some of them, and every one of them has had a very valuable input into this machine. Thank you very much. I hope you enjoyed the presentation and have a nice day.